that's our time complexity for the two function approach O of n square. Now that we understood the time complexity of this approach, now we can go and optimize it. Hi guys, how are you all doing? In this video, we'll take a look at path sum 3 problem. Difficulty level is medium. So let's see what the problem description is. So we're given a binary tree, and in that tree, each node represents an integer value. And along with that, we're given a target, and we need to find out the path or the subtree in that tree whose summation would be equal to that target. So if we take that example tree, let's say this example, then if we take nodes 5 and 3, then our sum would be 8, which is our target. If we take node 5 and 2 and 1, then again our sum would be 8. Or if we take node as -3 and 11, then our sum would be 8. So those would be the three paths that would give us sum 8. So we need to return the number of such paths that give us the target. So in this case, our return value would be 3 because there are 3 paths. And there are some limitations, like there won't be more than 1000 nodes, and the node values would be ranging between -1 million to 1 million. So doesn't mean much. It just means that there are 1000 nodes and we can potentially have integer variables hold all the sum and everything. We don't need to think about integer overflow and all that. So that's the problem. Let's see how we'll solve this problem. Okay, this is our whiteboard for path sum 3 problem, and we have this tree exactly same from the problem description, and our target sum is 8. So as we can see, there are 3 paths, 5, 3, then 5, 2, 1, and then -3 and 11. These 3 paths give us the target sum equal to 8. Now before we move forward with approach and solution, I want to clarify that this problem is about path and not subtree. I mentioned subtree in my problem description, but that's not entirely correct. So a subtree would be like 5, 3, 2. So this would be a subtree, but this is not a path. So what they say path is like path starts from any node and keeps going down only. So we need to find path. A difference would be like, let's say if they said like you have to find subtree, then it would be something like 2, 5, 3, -2. This would also give us 8. So that's the difference. So we need to find path and not subtree. So let's focus on finding those paths. This does look like a complex problem, but we'll go step by step. We'll first have a simple solution. We'll look at the time complexity, and then we'll try to optimize it. So let's do that. Let's try to solve this problem. Okay, so what we'll do is to implement this or to approach this problem, we'll try to implement this in 2 functions. So let's say we have one function as f1 and other function as f2. So let's first try to look at what we'll do in function 1, and then we'll go to function 2. So since the important part in this problem is that path can start from any node, it doesn't have to start from root, and it can end anywhere. It doesn't have to end in leaf node. So what we'll do is we'll have this function 1. What it'll do is for each node, it'll call this function 1 again, and it'll pass the same target. So let's say if this function 1 is called for 10 with target as 8, what this will do is it'll recursively call for all the nodes. So it'll call node 5 with same target 8. It'll call it for node -3 with same target as 8, and subsequently they'll call their children for the same function. So this is kind of starting function where each node will think that I am the starting node in that path and I need to find that target in my children path along with my value. So that's what this function will do recursively. So now all we have to do is we have to write function f2, which will start calculating the values, and then we'll have our count. So let's see how we'll do that. So now once this f1 is getting called for each node, what we'll do is we'll call f2 for that node, and we'll say start calculating the path, or start finding the path and try to find this target or sum. And that's how this will get started. So f2 will be called for 10, f2 will be called for 5, and likewise for each node. And then what we simply need to do is we simply need to add all this stuff and then return it. So let's see what we'll do in this f2 to calculate this path. So again, f2 is recursive function. So if node is null, then return 0, obviously. And we'll start counting how many paths are there whose target is equal to the sum. So obviously if node value is equal to sum, we'll say, okay, you know your node value is sum, so that's it, one path found. So count equal to 1. And then what we'll do, we'll calculate new sum, where sum minus node value, and then we'll say, okay, in the left tree, try to find this new sum, or in the right tree, try to find this new sum and give me all the path, and then return all those count. So let's take an example. Okay, so let's say for this 5 we called f2 and our target is 8. So what this 5 will do, it'll come here, obviously 5 doesn't match 8, so we'll go here. Our new sum will be 8 minus 5, which will be 3, and this will say node dot left and new sum is 3. So when it'll come here, it'll say, okay, node dot value is 3, count is equal to 1. So it'll like try for more children, but it'll not find, and it'll eventually return 1. So we'll find our one path. Once this is done, this will say, okay, find node dot right, which is here, find the new sum 3. Now this will go here, node value is 2, sum is 3, doesn't match, so I'll come here. Now new sum would be 3 minus 2, which is 1. So this is done, and our new sum is now 1, and we'll say, okay, this is null, so node dot right, new sum is 1, call it, and then this will call 1 matches 1, count 1, all the childs are null, so we'll return 1. So again we'll find one more path, and likewise we'll find this path also. So eventually we'll get our 3 count for this. So that's the implementation for this, breaking up into 2 functions, and function 1 is responsible making each node as the starting of the path, and then function 2 is responsible for calculating that sum in that path. So let's go ahead, let's write this code and run it and make sure it passes all the test case, and then we'll actually come back and we'll look at time complexity, and then we'll see if there is any optimization into it. So but let's write the code for this and let's submit this code. So this is our 2 function approach that we just did on the whiteboard. This is the actual code for this. So we have our initial path sum method, and we'll recursively call this method for the children of the current node, and we'll tell them that start finding the path for this target, and we'll do this for all the children so that each node thinks that it's the starting node in the path finding process. And that's what path sum 2 will do. It'll start finding the path for that particular target, and path sum 2 will simply take that node value, subtract it from the sum, and we'll call it for the left child or right child, whichever returns that path. We'll keep adding those count. So that's the code. Let's run it. Let's make sure that it runs for the sample test case. It does, and now we'll submit it and we'll see if it runs against all the test cases. Looks like it just finished, and it took around 21 milliseconds, around 42% faster than other submissions. So it looks like there is some scope for improvement. So before looking at optimization, what we want to do is we want to look at the time complexity of this solution and then think of optimization. So let's do that. So to understand time complexity for this approach, I've taken a different example. I hope this helps us understand time complexity much easier. I actually want to go into detail of this time complexity for this one, because I've seen, like, I was reading it and I've noticed like a lot of people have referred this approach, the two function approach, as O of n time complexity. It's linear, but I don't think that's entirely correct. Let's see what time complexity we can come up with. So we know the approach, we know that we'll call function 1 for each node, and then each node will call f2 function 2. So let's see what happens when we call f2 from 5. So we'll go down for each node and we'll try to find this target, right? We'll say 5, so we'll subtract 9 from 5. We'll say now we need to find 4, so we'll go here and we'll find the path as 9, but we'll still going down just in case if there are negative numbers and we can find more path, right? So if we call f2 for 5, we'll traverse 5 nodes, which is n nodes, right? Now we'll call f2 from 4 and we'll traverse 4 nodes likewise, which is n minus 1. Now for 3, we'll call 3 nodes and we'll traverse 3 nodes, which is n minus 2. And likewise, we'll do it for rest of the nodes. So this is our complete traversal, complete time or nodes it'll take to give us the output. So if you look at this pattern or this one, we know the formula for this summation, right? This is n into n plus 1 divided by 2, which is 5 plus 6 divided by 2, which is 5 into 6, sorry. So which is 15, right? So 5 plus 4 plus 3 plus 2, 1 is equal to 15. Now, if this is our time taken or this is our time complexity, what this comes to is n square divided by 2 plus n divided by 2. Now, when we have n square, we can ignore the linear part of it in terms of square, that's more prominent, and we can obviously drop the constant. So our time complexity comes to O of n square. So that's our time complexity for the two function approach, O of n square. Now that we understood the time complexity of this approach, now we can go and optimize it. So we'll look at optimizing this approach. We'll see if using some additional storage, can we come up with an approach which takes O of n time. So let's do that. So we go back to our original sample tree. Our actual target is 8, and we'll try to see if we can come up with an approach which is better than our previous approach. So over here we'll use a technique called prefix sum, but name doesn't matter much, right? I mean, really what really matters is how we can use it to solve this problem. So in this approach, what we'll do is we'll have a dictionary or hash map where we'll store the running sum of the path and we'll count how many times we've seen those values. So without talking much, let's actually first create that hash map and see how it looks like for the sample tree. Okay. This is the crux of this approach that will help us find that path whose sum is that target. So now let's say we have this dictionary and now we start traversing the tree again. I mean, in reality we'll be doing together, but just for simplicity we have this and now we are traversing the tree. So let's say we started traversing tree from here and we keep a variable called running sum. Now when we are here, our running sum would be 10. when we come here, our running sum would become 15. And when we come here, our running sum would be 18. So let's pause here and let's think about it. Now we know that this phi3 path is a valid path whose target is 8. So from this traversal, can we find this path using this dictionary? So now we've traversed 10 phi3 and our running sum is 18, right? And our target is 10. So the trick that we do is that from this complete traversal to get this target 8, is there a previous path that we can eliminate? So if we eliminate 10, then we get our path, required path, which is 8. So how do we find this 10 and how do we check if we ever hit this 10 or not? So what we do is we do obviously this running sum. I'll just write rs running sum will do minus our target. So this will be 18 minus 8 and 10. So that gives us 10. And how do we find out that whether was there a 10 in the path, like was there any previous 10 that, or was there any some path which had 10? We go to this dictionary. We say that this dictionary, do you have running sum minus target in your anywhere in your keys? So this dictionary says yes, there was a path or a node whose sum was 10. So if we find this, then we can say that yes, there was a 10 and we can remove that and we'll get our path. So we'll say that yes, that's the count we need. So we'll take count plus equal to 1 if we find this, right? So that's how we are using this dictionary to calculate the previous path that we can get rid of, or we can think of that yes, we had hit that value, and if we remove that from running sum, we'll get our path. So let's make sure that we see it for one more example. So same for this path, right? So 10 phi 2 1, again this is 18. So we'll again do running sum minus target, 18 minus 8, 10, and we'll say yes, we had seen 10 and we want to remove it. So there was one path where it was 10, so we'll do plus 1. And then same for this path also, right? 10 minus 3, which is 7, and then 11, which is 18. So we'll do again same thing and we'll do plus 1. So we'll get our total 3 path. So we're using this dictionary to find out that was there a previous path whose, if we can remove that path, we'll get our target. So we do running sum minus target to get that previous path. And if there was a previous path with that value, then we can say that yes, we can make a path which is equal to 8. So we'll use this approach to optimize our previous implementation. Now what we'll do is we'll traverse the tree only once. As I said, like we'll be calculating this dictionary and we'll be doing this calculation at the same time when we are traversing the tree. So our time complexity would be O of n, where n is the number of nodes. Our previous approach had time complexity of O of n square, and this would be O of n. So when we actually submit the code, we should see some improvement. So there is one more thing which I want to point out. In the initial part of the video, we differentiated between subtree and path. So that differentiation is important here. So I just created a crude and simple explanation, but in reality what we need to do is when we are traversing this path, we'll be obviously calculating this dictionary and everything, but once we finish this path, we'll start traversing this path, right? And this path and this path. So what we need to make sure is when we are done traversing this path, we need to remove these values from dictionary. So 10 phi 3 3, which is 21. So once we are done traversing this path, we need to make sure that we remove 21. When we are done traversing this path, we need to make sure that we remove 15 from the dictionary, or we reduce it by 1, right? So that when we are calculating or when we are removing the previous path, we don't hit those values, right? So that's the important part to understand between path and subtree. If we had to find a subtree, we would have done different logic. So that's a little bit of backtracking, removing values from dictionary. So I'll actually show you when we actually go to the code on how we are doing that. That's simply just like once the function completes, subtract that value from dictionary by -1. So let's go to the code. Let's see how actual code looks like, and then submit it, and let's see if we get any. Our final code for the hash map based approach. We have our hash map declared here, and then we call our pathSum2 function where we start running sum as 0, and what we do, we add the root value into running sum, and then we try to find out count, where if we can get rid of any previous path and get the required path. So we do running sum minus our target. So if you remember our whiteboard, we did like 18 minus 8, which was our target, and we found out 10, and we had a path previously where 10 was there. So we say that if we find that, then we found one valid path, or however many number of valid paths are there. And then we increment our map with current running sum, and then we subsequently call pathSum2 for left child and for right child. And the remaining part that I said I will show in the code is the backtracking. So once we are done with the current node and all its children, what we do is we remove that value, or that running sums count we reduce by 1. Hence we remove that node from our map, and when we move to the other part of the tree, we don't account for this node. So that's how we backtrack and make sure that we are doing path and we are not doing subtree. So that's what takes care of it, and eventually we return the count. So one thing we didn't talk about was we are adding an arbitrary value in the map. We are saying that for running sum 0, just add 1 straight away. Now what this will do is this will take care of the root node whose value is equal to sum or target. So let's say if our target is 10 and our root node is 10 itself, then we'll come here, we'll make running sum as 10, and we'll say running sum minus target, 10 minus 10, which is 0. Is there any key which in dictionary which has value 0? Then we'll say yes, there is 1, and that'll be our count, and then we'll say that's a valid path. So root node itself can be a valid path, and that's what this dictionary arbitrary value or map arbitrary value is. So adding 0 and counting it for 1. So that will take care of root node. So that's it, guys. Let's run the code, make sure that it passes the sample test, and then submit the code, and then run against all test cases, and let's see how long it takes. So let's see. So it took 2 milliseconds. It's faster than 100% of all the submissions. So there you go, guys. The time complexity of this approach is O of n, and the previous 2 function approach is O of n square. So I wanted to show both the approach so that you guys have complete understanding. And even though we have seen this approach, I know this is complex and tricky to like visualize it and imagine it, because we're removing the previous path from dictionary and we're traversing the tree and we're calculating the dictionary. Everything is happening at the same time. So just take this code, like I'll put the link in the description below, run it, or if you have whiteboard or if you have notepad and pen, draw out a different tree of your liking and run that tree against this code and try to figure out why it works the way it's working, and then you'll guys get a feel of it. So try to do that. Let me know if you guys still have confusion, questions, let me know in comments, or if you have any suggestion, any better approach, let me know in comments. And then the usual part, subscribe, like, and hit that bell icon for notification. And I'll see you in next one.